Have you ever wondered how we confidently make important decisions based on data, especially when there's always a degree of uncertainty? Imagine you are building a new machine learning model and want to determine if its performance is truly better than an existing one, or if any observed improvement is just due to random chance. How do you draw a clear line between what is significant and what is merely noise? The significance level, often denoted by the Greek letter alpha, directly affects hypothesis decisions by defining the critical threshold for rejecting the null hypothesis. It is the maximum acceptable probability of committing a type 1 error, which means incorrectly concluding that there is an effect or relationship when, in reality, there is none. A lower significance level demands stronger evidence to reject the null hypothesis, making it harder to claim a discovery. The core mechanism behind this impact lies in the trade-off between different types of errors. When you set a significance level, you are essentially establishing the acceptable risk of a false positive. A very low alpha, for example, 1%, means you are highly cautious about rejecting the null hypothesis. While this reduces the chance of a type 1 error, it simultaneously increases the risk of a type 2 error, which is failing to detect a real effect. Conversely, a higher alpha, like 10%, makes it easier to reject the null but at the cost of a greater chance of a false alarm. In practice, choosing a significance level involves considering the consequences of these two types of errors within your specific domain. For instance, in medical research, where a false positive could lead to an ineffective treatment being adopted, a very stringent significance level, such as 1% or even 0.5%, is often preferred. In exploratory research, where the goal might be to identify potential areas for further study, a slightly less strict level, like 10%, might be deemed acceptable to avoid missing interesting preliminary findings. A key concept intertwined with the significance level is the p-value. The p-value represents the probability of observing data as extreme as, or more extreme than, the data you collected, assuming the null hypothesis is true. You reject the null hypothesis if your calculated p-value is less than or equal to your predetermined significance level. This relationship provides a clear decision rule for your hypothesis test. While 5% is a common convention, it is not arbitrary. It represents a widely accepted balance between type 1 and type 2 error risks across many scientific fields. Ultimately, understanding how the significance level works empowers you to make informed and defensible statistical decisions. It allows you to consciously manage the risk of making an incorrect conclusion, ensuring that the insights you derive from your data are robust and appropriate for your research question or machine learning problem. This careful consideration of alpha helps to build confidence in your findings and the models you develop.